1, 2, 3. Test warahmatullahi wabarakatuh, and hi to everyone. So welcome to subject of electrical machines, particularly chapter number 1 with title of machinery principles. So by the way, I'm Mahyuzi Benjina, so you can find me at this email, mahyuzi@ethsm.edu.my. So list of motivations. The course presents basic engineering knowledge by teaching conversion of electrical energy to mechanical energy and vice versa. So concepts of energy transportation. So basically this is the basic knowledge or the fundamental knowledge of the electrical machine. Right. So we might see how the conversion of electrical energy to mechanical energy and vice versa, as well as the energy transportation concepts, okay, where every electrical engineer needs this basic knowledge. So what's come to more interesting part is the automation of manufacturing, which has increased the use of computer control and electronically regulated electric motors. Okay, then manufacturing and utility industry need well-trained engineers familiar with motors and energy transport. All right, so this is when we come to application, the real-life manufacturing, where the industry out there actually require well-trained engineers who are familiar with operation of machines. And then some of the learning outcomes. At the end of this topic, student will be able to know the fundamental concepts of magnetic fields. Basically, this is the basic, I would say the fundamental concept, okay, of a machine. And then point number 2, understand the general principle of magnetic field. Again, we are going to emphasize on this particular element. And then point number 3, able to solve basic problems related to magnetic circuits. So all here will mainly focus on magnetic field as well as the magnetic circuits. Okay, outlines of the entire chapter. First, we are going to see the rotational motion. So Newton's law, in terms of Newton's law, and also the power relationship. Before we move on to the magnetic field, so the definition, so the orientations, the behavior, etc., etc. Okay, and then what is going to we're going to see again another law, namely Faraday's law. So from here we may see the induced voltage from a time-changing magnetic field. So what happens if we do have a magnetic field that is respected to time changing, all right, and out of there voltage is induced. Okay, and then production of induced force on a wire. So we have a conductor, we have a wire. So this conductor is a current carrying wire, and from there we might see force is induced. Okay, and then induced voltage on the conducting moving in a magnetic field. So in the presence of a magnetic field surrounding the conductor, which is a moving conductor, and from there we might be able to produce or induce voltage. Okay, this is some of the principles we are going to discuss. So magnetic poles versus a geographic pole. All right, so this is Earth's. Okay, this is the compass. So this is the North Pole and this is the South Pole geographically. All right, so but once you see the compass, it shows the different or the opposite direction of magnetic fields. Okay, so the North geographic pole over here. So this is again the magnetic pole. So this is magnetic poles representing the North Pole as well as the South Pole. Again, this is for geographic pole. Okay, comes to a compass. So we have north, of course, this direction as well as the south. By the way, principally, so we can see that magnetic field is actually going out of North Pole and coming into south. So this is the orientation, the direction of the magnetic field. Okay. So similarly, you can see from a compass, it must go from north to south outside the magnetic bar, for example, and then inside this magnetic core, you see the flux is, or the magnetic field is actually flowing from south to north. Okay. Now here, similarly, we have south to north. Okay. Then this is how the magnetic bar, let's say, reacts to its poles. Okay, we have a similar pole over here, let's say S to S. So how they react? So of course, repulsive action. Okay, see, and then what happens if you have a different pole? So south and north. So attractive actions. Okay, this is quite common. Like poles repel, and then unlike poles attract. Here, okay, again. And then jumping over to the next slide, so you see the right hand grip rule. So we have our conductor over here. Okay, inside this conductor we have a moving, or we have a flowing current, for instance, and then out of this magnetic fields will be induced surrounding about the conductor or the current. Okay, so this is a basic magnetic field with respect to the current, and this can be represented by this rule. Okay, the right hand grip rule. Okay, and then yes, this, your thumb is representing, okay, you have straight upward over here. Okay, straight upward over here is representing again your conductor. All right, and then the rest of your fingers, okay, are actually representing the direction or the orientation of the magnetic field. Okay, we call it B, the magnetic field density, and this is I, stands for current. Okay, representing current. And then once you wave your fingers, these 4 fingers inward, for example, and this will show the direction of the magnetic field. Okay, that react to the, again, direction of the current. Okay. So if the direction is downward, for example, of course it will give a different direction of magnetic field. Okay, according to this, again, the right hand grip rule. So flux formed by a current loop. So we have, again, this is the right hand. So this is the this is representing your magnetic field density, and then we have your dry cell, for example, over here. You have your supply over here, for example, with positive and negative terminal. So this current is flowing inside the conductor back to the negative terminal, and from there, when you apply the right hand rule over here, you will see that all these orientation are actually representing. The red line one here is actually representing the direction of magnetic flux. Okay, of course, subjected to the direction of the current. Right? All these are the direction of the current. So similarly, if you have this diagram, for example, so we have the blue line one, which is in the different or opposite direction, because we do have the different direction of current. Okay, and then this is again applicable from or by the right hand rules. Okay. So we, again, the magnetic field produced by a loop current. Okay. So what about the Fleming's left hand rule? So let's say you have your left hand with this one, or finger number 1, finger number 2, as well as finger number 3. So the thumbs is representing motion or force. Then finger number 2, your pointing finger representing field or lines of flux. Okay, this is the notation B. Okay, and then your middle finger is representing current. Okay, all these are representing the direction for each element F, B, and I. So this is how we can easily remember or memorize the rules. So by having FBI or the Federal Bureau of Investigation. So some of the application you can see here with the presence of magnetic field. So the magnetic field is actually produced by this magnetic bar. Okay, we have N and South pole. Okay, so magnetic field again always flow from north to south. Sorry, so north to south over here. Okay, this is represented by your pointing finger, the one in green. Okay, field. And then your current is flowing in this particular conductor. So this is the direction of current. Okay, moving this direction. And now you can obtain the direction of motion of force once you apply Fleming's hands rule. Okay, so you have your again current over here. Okay, and then you have field, magnetic field direction from N to S, and then you might see the motion or the force is actually moving upward. Okay, here and here, moving upward. And then effect of current through a magnetic field. Again, take your left hand over here, for example. Okay, and then you apply FBI, the force, the magnetic field as the current into this simple experiment. Again, you have the C called magnetic bar over here, for example. So we have magnetic field flowing from N to S again. So magnetic field N to S, or into the page, you can see the cross or the X symbol over here. This means the currents. So in the same color, okay, blue color, all these are representing the magnetic field. So the blue color is flowing into the page. Okay, so into the page, and then we have current. This is current at initial stage, which is 0 ampere. And then this is the B into the page, okay, the magnetic flux density. And once we inject current I, okay, upwards, and with the presence of magnetic field, so we can see immediately the force acts to the conductor, and now it is moving to the left. Okay, so this is actually the force, all right, motion, which is generated by the reaction between I and magnetic field. Okay, again from here, okay, the motion or the force, okay, represented by your thumb finger. Okay, so similarly, if the direction of the current is moving downward, okay, we see with the same direction of magnetic field over here, all here, and then now we have an opposite direction of force, which is to the right. Okay. Again, another application of right hand rule. So we have our battery pack over here. So we have positive and negative terminal. So this is the current direction flow into the magnetic fields. Okay, N to S, and by again applying the right hand rule over here, okay, FBI, you will see that the force is moving downward. Okay, so once you change the direction of I, okay, you will see again the force is going upward. So rotational motion and Newton's law. So just imagine this is our example of machine. So let's say this is an induction motor. Okay, just for instance, so this is the construction inside the unit, and then we have the shaft over here, right? So we have the stator part. Okay, we have the middle one, which is the rotor part. So we do have the blade as the fan. Okay, we have this fin for cooling, and then we have the terminal over here. Okay, the three-phase, I believe, terminal. So these are the casing. So this is the base, etc., etc. So the basic construction of a machine. All right. So this is how the rotor spin. So inside the compartment. So what about the representation of the direction of this particular rotor? Okay. So an electric machine consists of, yeah, this is the basic construction. We do have the rotor, stator, as well as the shaft. Right, so then direction of rotation, so counterclockwise CW, so we assign it as positive. Okay, and then the clockwise CW, so this is negative. So we have the clockwise direction, for example, like this, here, so this is negative, and for the counterclockwise, okay, vice versa, we have a negative over here, right? Oh, sorry, this is positive, negative. Okay, positive. So rotational motion versus linear motion. So we have some of the equations, some of the rules and the regulation. We compare between the rotational motion and also the linear motion. So we have seen for common linear motion, linear distance R. Okay, we have displacement over here. This is the reference. So this is the beginning point, the reference. So we have a shift, we have a displacement of R, okay, in meters, the unit, for linear motion. This is a very straightforward discussion. So what about the rotational motion? So when we come to rotational motion, so the similar displacement is now becomes a angular position, theta. Okay, so no longer meters, it's theta, since it spins or rotates in radian of or degree. So similarly, we have the reference, and we have a displacement in rotation here to here, and represented by theta. The angular position. Okay. So the velocity, linear velocity. So once we have the linear distance, with respect to times, what happens if these displacements changes, okay, in times, or with respect to time? So we might have the linear velocity, v. All right. So the unit is meter per second. So we can derive from there that v is actually equal to dr over dt. Okay, the displacement of distance over time changing. Okay, then similarly, if come to the rotational motion, so the angular velocity, so omega, okay, the unit is radian per second. So we do have the displacement again in rotational, changes in data over times. Okay, and then here we have the Fm is actually a revolution per second. Okay, omega m over 2 pi. Okay, this is how we relate between the revolution per seconds with the omega m, or the angular velocity. And to add to that, so we have nm, the revolution per minute, okay, which is we have 60 multiplied by fm. So since we know that 1 minute equivalent to 60 seconds, so multiplied by 60, we can obtain the speed or the angular velocity in revolution per minute or RPM. See, what about the linear acceleration? So again, we have we can derive from above equation for the linear velocity that is again changes over time. Okay, dt. So we have again d1 v1 to v2. So the speeds or the velocity change. Okay, we time, for example, in 3 seconds, for example, and then from there we can derive to get or to obtain the linear acceleration with unit of meters per second square. Okay, this is the acceleration. So same goes to angular acceleration. So alpha, so radian per second square. This is the unit. We have so the alpha equal to d omega over dt. Okay. And then what about the force? So according to Newton's second law, okay, the second law or the second principle. So we have, for example, a mass. Okay. This is the surface connected to the surface. So we have force F. Oops, I forgot the M. So this is a mass. Okay, of this object. So we do have the force, for example, the A here. Okay, the acceleration. Okay. So this is from Newton's second law. Okay, so we have M and A, the speed of the object, okay, M, and then we have the force that induced or generated by this direction, okay, M and A. Then the torque here in rotational motion is given by this equation, or this equation, F equal to R sine theta. So this is the rotational motion. So we have a force over here. So give a force at this particular point, for example, and we try to extend or try to prolong the action of the F into the middle, somewhere in the middle of the rotational motion. Okay, and then we try to make or to create a perpendicular action between this point and also this F. Okay, and then from there, this vector is usually represented by R sine theta. So F here multiplied by R sine theta. So this is a given torque. Okay, the unit is Newton meter. So Newton's law of rotation, torque equal to J alpha. So theta is the net applied torque. Okay, we have net applied, which is torque in Newton meter or pound feet. So what about J is the moment of inertia in kg meter square or slug feet squared. So this is similar to M in linear here, in linear motion. All right, here, this is the example. Okay, this is equal to M. So this alpha is actually what? So this is actually the resulting angular, okay, angular acceleration in radians, all right, per second square. So you have seen this in earlier page, okay. So here, angular acceleration. Okay, and then what else? So the J is again identical to M in linear motion. So this force is applied to an object and resulting angular acceleration. Okay, and then the work here is defined by the integration of torque d theta. Okay, and then if torque is constant, then we have a straightforward relationship between work, torque, and theta. So however, work in a linear motion, so we can define it as a application of force through a distance. So we have actually W equal to integration of F. This is in linear, so we try to make a comparison to have a better understanding. So over R, so this is the resistance, change in resistance, this is the force. okay, that apply to the object. And then the force collinear with direction of motion. Okay, so the unit is of course in joule. Okay, don't get confused. Again, I mentioned this only for linear. Okay, this is for linear. However, when it comes to rotational motion, so this is how we relate. Okay, between again work, torque, and also theta. So power unit in watts, okay, or joules per second. The unit watt or joules. Okay, let me write the unit, okay, per seconds. And then what is division of power? Rate of doing work. And then increase in work per unit time. So we have over here omega, again, this is equal to dt over d theta, sorry, over dt. So this is how we derive from P, which is the rate of doing work. Okay, the rate of doing work. So we have the omega or W, sorry, over dt. So we know that omega or W equal to T. And then rearrange, we have torque over here d theta over dt, and d theta over dt is actually omega. All right, so omega is, yes, here is the angular velocity. Remember, the unit is in radian per second. Or in a similar form, we can simply write that P in angular rotational motion is equal to torque omega. Okay, and then of course the unit is what? P in watts. So this is the unit, torque in Newton meter, and omega is radian per second. Okay, this is how we write the equation in terms of watt and in terms of horsepower. So again, this N here over here, this is what? This is RPM. Okay, revolution per minute. So this is how we do the conversion. Okay, and then if you want to have in horsepower, okay, so you need to have pound feet unit and RPM over 52552. Okay. All right, thank you very much for your time. So I will continue this discussion in the next video.